A complex modern electric power transmission system links many power generating plants into a network called a grid that supplies electricity to meet the requirements of a city, part of a country, or even an entire continent. Each generating unit contributes to the total amount of power that is available across the grid. All generators use induction to create an output voltage. When the output of a generator is connected to a circuit, the induced voltage causes current to flow through the circuit. There are three requirements for inducing voltage. First, a conductor must be available to carry current. The second requirement is a magnetic field. Third, there must be relative motion between the conductor and the magnetic field. In this illustration, a wire is wrapped around a metal ring. The wire serves as the conductor that carries the current that results from induction. The second requirement, a magnetic field, is created using a magnet. A permanent magnet like this one can be used to induce voltage, but the magnetic field it creates is very small. Electromagnets are used to create controllable magnetic fields that are strong enough to induce large amounts of voltage. This is a basic electromagnet. It consists of a coil of wire wrapped around a metal bar or core. When electric current from a source of direct current flows through the wire, a large concentrated magnetic field is created. The wire may be referred to as the field winding because it helps to create the magnetic field. The third requirement for inducing voltage is relative motion between the magnetic field and the conductor. Here's an illustration that shows how voltage is induced when the electromagnet rotates. This electromagnet has a north pole and a south pole. The magnetic fields at the two poles are opposite in polarity. As the electromagnet rotates, the magnetic fields cross the conductor and induce a voltage. We can say that the north pole induces a positive voltage and the south pole induces a negative voltage. Generator output can be represented as a sine wave that is plotted on a graph. On this graph, the vertical axis represents the strength of the voltage, which can be positive or negative. The horizontal axis represents time. As the electromagnet rotates, the relative positions of the electromagnet and the conductor affect generator output as shown on the graph. When the electromagnet is vertical and the magnetic fields don't cross the conductor, the voltage is zero. Now, as the electromagnet rotates through the first quarter of a complete revolution, the output increases to maximum in the positive direction, and then drops to zero again as the magnet reaches a point 180 degrees from its starting position. As rotation continues, the output reaches maximum in the negative direction as the south pole of the magnetic field crosses the conductor. The output decreases again as the magnetic field moves away from the conductor. Let's expand the simplified illustration of a generator to show some other components. The metal bar and the wire that is wound around it can be called the rotor core. In the illustration, the rotor core is connected directly to a DC power source that appears to rotate with the core. However, the DC power source for a generator is usually stationary. One way to cause current flow from a stationary DC source to the windings that encircle the rotating metal bar is to use slip rings and brushes. The slip rings are usually made of copper and they turn with the generator shaft. One slip ring is connected to the negative lead of the rotor winding, while the other slip ring is connected to the positive lead. Inside a generator, the slip rings, the rotor core, and the wires connecting the slip rings to the windings all rotate together. The brushes are typically made of a carbon material that brushes against the slip rings as they rotate. Current flows from the negative side of the DC power source through one brush to a slip ring. From there, the current flows to the winding around the rotor core where it creates a magnetic field. To complete the path, the current flows from the winding to the other slip ring, then to the brush, and back to the positive side of the DC power source. The component of the generator that doesn't rotate can be referred to as the stator. The conductor that is wound around it can be called the stator winding. The ends of the conductor are connected to the power system. The output from the generator we've been looking at is single-phase voltage. Single-phase means that there is only one voltage output. This is because our example has only one stator winding or conductor. However, most generators used in power plants are designed to produce three-phase voltage. Let's see how a three-phase voltage output can be produced by modifying the simplified generator illustration. If we add two more stator windings, voltage will be induced in each winding as the magnetic field crosses the wires. The result is a three-phase output. As the rotor rotates, maximum voltage is induced in each of the three stator windings at different times. This sine wave represents one of the three phases. Maximum positive voltage occurs as the field around the north pole of the electromagnet crosses the first stator winding. Maximum voltage in the second phase occurs as the field crosses the second winding. At this point, the first phase voltage is decreasing. In the third phase, maximum voltage occurs as the field around the north pole crosses the third stator winding. Now, the south pole's magnetic field has crossed the first winding, inducing a negative voltage. As rotation continues, each of the three phases produces alternating positive and negative current that is constantly changing. Here's how the three output voltages look on a single graph. We can see that because each of the three phases produces a voltage, the total output is never zero. This means that a three-phase generator is more efficient than a single-phase generator of similar size. Most generators in the United States produce alternating current at a frequency of 60 cycles per second. This graph of a sine wave represents one cycle of alternating current. A cycle starts with the voltage at zero. To complete one cycle, the voltage increases to the maximum positive value, drops back to zero, then increases to maximum in the negative direction. Finally, the voltage returns to zero again. The rotor has completed one revolution, and both the north and south poles of the rotor's magnetic field have crossed the stator winding in the generator. The number of cycles that occur in 1 second is the generator's frequency and is measured in hertz. So 60 cycles per second equals 60 hertz. It's important for a generator's speed to be consistent. Equipment that uses or produces electricity is usually designed to operate at a specific frequency. If the frequency changes, the equipment can be damaged. There are two factors that control the frequency of the current that is being generated. One is the speed at which the rotor turns. The other factor is the number of magnetic poles in the rotor. In this illustration of a simplified generator, one cycle of current is produced for each revolution of the rotor, so the frequency equals the speed at which the rotor turns. In order to produce 60 hertz, a generator's rotor has to make 60 complete revolutions each second, or 3,600 revolutions per minute, abbreviated RPM. But not all generators are built like this one, with one north pole and one south pole. In this example, there are two north poles and two south poles, so that each revolution produces 2 cycles of current. In this case, the rotor only has to make 30 revolutions in a second to produce 60 hertz. That's 1,800 RPM. Now, under normal operating conditions, The rotational speed of a generator will not change. A generator must operate precisely at its rated speed in order to maintain the required frequency of 60 Hz. If the load or the demand for power across the grid exceeds the capacity of all the running units, all the generators on the grid would slow down slightly, reducing the output frequency. When this happens, the dispatchers who control the output of all generators in the power system follow specified procedures to quickly de-energize or shed some of the customer load. These steps should restore the normal 60 Hz output and protect equipment in the system from damage. In an emergency, if frequency drops below a certain level for longer than allowed by plant operating standards, the plant might have to be taken out of service to protect the turbines, generators, and auxiliary equipment, as well as the equipment of the customers served by the grid. Here's a graph that shows how the demand for electricity across a power grid can vary during a typical day, as customers turn electrical equipment on and off. As the demand changes, the electrical output of a plant's generators has to be increased or decreased. The output of a generator can be adjusted by adjusting the strength of the magnetic field. To do this, the amount of current that is supplied to the generator's rotor windings is increased or decreased. Since this current is small, it's easy to control. In this simplified illustration of a generator, the device that produces and supplies current to the rotor windings is called an exciter. Direct current is used because it is constant, and it produces a steady, unchanging magnetic field. While several different types of exciters may be used in generators, the two types that are used most commonly are DC exciters and brushless exciters. We'll look at the DC exciter first. A DC exciter is basically a small generator. The exciter has a rotor and rotor windings, and it has a stator and stator windings. The exciter is different from the generator because the magnetic field is created in the stator windings of the exciter, rather than in the rotor. Another difference between the exciter and the generator is that in the exciter, voltage is induced in the rotor windings as they cut across the magnetic fields around the stator. Like the generator, the exciter uses an electromagnet for the magnetic field. The source of power for the electromagnet is a pilot exciter. The pilot exciter includes a stator with a permanent magnet instead of an electromagnet to provide a magnetic field. A permanent magnet has a relatively weak but permanent magnetic field. The pilot exciter also has a rotor with rotor windings. And a commutator. A commutator is a device that changes alternating current into direct current. The rotors for the generator, the DC exciter, and the pilot exciter are all turned by a common shaft that is rotated by a turbine. When the shaft turns the rotor of the pilot exciter, a small voltage is induced in the rotor windings. This voltage produces an alternating current at the pilot exciter commutator. The commutator converts the alternating current into direct current. The direct current flows through the stator windings of the DC exciter, creating a stronger magnetic field. When the shaft turns the rotor of the DC exciter, a moderate voltage is induced in the rotor windings. This produces an alternating current at the exciter commutator. The commutator converts the AC into direct current. Now the direct current flows through the slip rings of the generator and through the rotor windings, creating a strong magnetic field. And finally, as the generator rotor turns, a large amount of voltage is induced in the generator stator windings. It is this voltage that goes through the transformers and is transmitted to consumers through the power grid. Notice in the illustration of this generator and exciter system that there are no brushes or slip rings. That is why this is called a brushless exciter. This part of the system is the generator. This component is a rectifier bank that is mounted on the shaft and rotates along with the generator and exciter rotors. The system also includes an exciter, a stationary rectifier bank, and a device called a permanent magnet generator. This device is very similar to a pilot exciter, except that the rotor is a permanent magnet and voltage is induced in the stator windings rather than in the rotor windings. As the shaft turns the rotor of the permanent magnet generator, a small voltage is induced in the stator windings. This produces an alternating current that flows to the stationary rectifier bank. The rectifier converts the alternating current by dropping the negative half of the cycle. The direct current flows through the stator windings of the exciter, creating a magnetic field in the stator windings. The magnetic field is used to induce alternating current, this time in the exciter's rotor. The alternating current is then rectified to direct current by the rotating bank of rectifiers. This direct current creates a magnetic field around the generator rotor, which is used to induce voltage in the stator windings. So, in a brushless exciter, the entire process of creating magnetic fields and inducing voltages from the permanent magnet generator to the main generator is performed without the use of brushes or slip rings. When a new generating plant is constructed, the generators often are equipped with microprocessor-based exciters. This type of exciter is easy to maintain and control. The microprocessor-based exciter can also be retrofitted to older generators in place of other types. Inside a generator, several factors can contribute to the creation of heat. These include bearing friction and fluid friction. But the greatest source of heat in a generator is current flow. Most of the parts inside a generator can withstand only a certain amount of heat. Above 250 degrees Fahrenheit, for example, most insulating materials begin to break down, which can cause electrical faults. This means that the operating temperature inside the generator must be carefully monitored and controlled. This small generator is called an exciter. One way in which heat can be removed from a unit like this is to draw or blow it out with air. In an air-cooled system, air is drawn in through filters on the generator casing, and then it circulates around the moving parts inside. The air absorbs heat from the generator components and carries it out through vents to atmosphere. Now, air cooling is sufficient for smaller generators. Larger generators, though, create far more heat and require more cooling capacity. So a cooling system that uses hydrogen gas is often the solution. Hydrogen is capable of absorbing about 7 times more heat than an equal amount of air. This means that a generator can be cooled more efficiently with hydrogen than it can with air. Another advantage is that a large hydrogen-cooled generator can be housed in a smaller casing than a similarly rated air-cooled generator, so less space is required. One of the problems with hydrogen is that it can explode when it's mixed with air in certain concentrations. The slightest spark can ignite the mixture if it contains from 4% to 75% hydrogen. If there's more than 75% hydrogen in the mixture, however, there's not enough air present to support combustion. So, to maintain optimum efficiency and safety inside a hydrogen-cooled generator, the hydrogen concentration is usually kept above 95%. When a generator is cooled with hydrogen, the hydrogen gas is pressurized and sealed inside the generator so that it doesn't mix with air. This means that the heat has to be removed by a cooling system. This generator has 4 hydrogen coolers, located on the sides near the top. Each hydrogen cooler is basically a shell-and-tube heat exchanger. Cooling water flows through the tube inside each cooler and absorbs heat from the hydrogen. Let's look at an illustration of a typical hydrogen cooling system. The illustration shows a series of hydrogen coolers. Oil seals are used at each end of the generator's rotor where it comes through the casing. These seals prevent hydrogen from leaving and air from entering the system through the openings. The rotor is surrounded by the stator. In this illustration, the stator has been cut away so that the rotor is visible. Two circulating fans are mounted on the rotor shaft. The circulating fans push hydrogen through holes in the rotor and pass the stator. After it passes through the coolers, the hydrogen returns to the circulating fans to go through the cycle again. The two types of systems that are generally used to deal with the hot water produced in the tubes of the hydrogen coolers are closed systems and open systems. In a closed system, the hot water from the coolers is directed to another set of heat exchangers, where the heat is removed. Then the cooled water is recirculated to the hydrogen coolers. When an open system is used to provide cooling water, the heated water is returned to its source, which is often a lake or a river. In most cases, the temperature of the hydrogen inside a generator is maintained at about 105 to 110 degrees Fahrenheit, or about 40 to 45 degrees Celsius. To adjust the temperature of the hydrogen, an automatic control valve is used to increase or decrease the flow of cooling water through the hydrogen coolers. In many plants, the hydrogen inside the generator coolers is kept at a higher pressure than the water. In case of a leak, water won't enter the generator casing. If a leak develops in this type of system, traces of hydrogen can be detected in the cooling water. In some plants, the cooling water is maintained at a higher pressure than the hydrogen. If a leak develops, traces of water appear in the hydrogen. A large leak could result in damage to generator components. Operators can examine a device called a liquid detector to check for water inside the generator. No matter how it's detected, a leak in the hydrogen cooling system means that the operating personnel must follow plant procedures to take the cooler and possibly the generator out of service so that repairs can be made. Even though the casing of the generator is sealed so that the hydrogen is contained inside, there are openings where the rotating shaft passes through the casing at each end. An oil seal keeps the air outside from mixing with the hydrogen inside. Here's how one type of oil seal works. Treated seal oil, supplied by a cooling and filtering system, is pumped into the center of the seals. Part of the oil flows toward the hydrogen side. Any hydrogen that is absorbed by the oil is carried to a container called a detraining tank. If the pressure in the seal oil system drops for any reason, hydrogen might be released into the atmosphere or into the air side of the oil seal. To prevent a drop in oil pressure, the seal oil system is equipped with a backup circulating pump that may be battery-powered. The rest of the oil flows toward the air side and carries the air into another detraining tank. After the air and hydrogen are separated from the oil and vented to atmosphere, the seal oil is recirculated to a vacuum treatment tank. To ensure that the oil continues to flow through the system, a circulating pump maintains the oil at a slightly higher pressure than the hydrogen. The difference between the oil pressure and the hydrogen pressure is called the pressure differential. The plant operator can adjust the control valve in the seal oil supply line so that the proper pressure is maintained. To maintain the required concentration of hydrogen in a generator cooling system, hydrogen has to be added to the system from time to time. The hydrogen may also have to be replaced entirely after maintenance work is performed on the generator. This illustration shows a typical hydrogen supply system. Piping connects the generator to the hydrogen supply, which can be cylinders or a bulk storage tank. Between the supply source and the generator is a series of valves. First, a pressure control valve is used to maintain the supply pressure from the cylinders at about 100 to 125 psig. For safety, isolation valves are used in addition to the control valves to shut off the flow of hydrogen completely. A second automatic pressure control valve maintains the pressure at which hydrogen is supplied to the generator at a lower value, 30 psig in this case. The piping carries the hydrogen to a manifold inside the generator. From there, it is dispersed within the generator casing. When hydrogen is used in a generator cooling system, supporting or auxiliary devices are required to help plant personnel monitor and maintain the generator. Typical auxiliary devices include purity analyzers, core monitors, hydrogen dryers, and liquid detectors. For the safest and most efficient operation, the hydrogen in a generator is typically maintained at more than 95% concentration. The instrument that is used to monitor the concentration of hydrogen in the air inside a generator is called a purity analyzer. Purity analyzers are equipped with an alarm to notify plant personnel when the hydrogen concentration decreases below a predetermined value. The generator usually has to be shut down if the hydrogen purity level cannot be maintained. If the cooling system doesn't function properly to remove heat, the excess heat can cause the insulating material inside the generator to break down, which can lead to electrical faults. When the insulating material begins to decompose, small particles are produced that are picked up by the hydrogen. These small particles are commonly called particulates. Inside the generator cooling system, a small sample of the circulating hydrogen is forced into a device called a core monitor. At predetermined intervals, the core monitor measures the concentration of particulates in the hydrogen and records the measurement on a strip chart recorder. If the concentration of particulates is significantly different from normal, the core monitor usually initiates an alarm. Depending on plant procedures, the generator may have to be shut down to prevent damage. Another auxiliary device that is often part of a hydrogen cooling system is a hydrogen dryer. This illustration shows the parts of a typical hydrogen dryer. In this system, hydrogen flows from the generator through an inlet valve into the dryer. After the hydrogen is dried, it returns to the generator through the dryer's outlet valve. Inside the dryer, the hydrogen is forced through a material that absorbs moisture. This material is called a desiccant. One type of desiccant that may be used in a hydrogen dryer changes color as it absorbs moisture. An observation glass allows plant personnel to observe the color of the desiccant. If the desiccant is dry, its color will be blue or white. When the desiccant becomes saturated with moisture, it turns pink. Moisture is typically removed from the desiccant using a procedure called regeneration. In your plant, the specific procedure for regeneration may vary, but it generally consists of 4 steps. First, the dryer is isolated from the generator by closing the inlet valve. Next, the hydrogen must be safely removed from the dryer by venting it. Then a fan and a heater are turned on to dry the desiccant. And finally, the dryer is returned to service by reversing the procedure. If excess moisture collects inside the generator casing, it could cause electrical faults or damage to components. A device called a liquid detector is usually connected at the bottom of the generator casing, so that any leaking moisture will drain into the detector. If the level of liquid inside the detector exceeds a predetermined value, an alarm is energized. Some detectors are equipped with an observation glass that allows operators to check the liquid level inside the detector. In many plants, The drain valve at the bottom of the detector is opened periodically to remove accumulated liquid. Before the drain valve is opened, however, the inlet valve to the detector must be closed. This helps prevent hydrogen from escaping through the drain valve. If excess liquid accumulates over a short period of time, it might indicate a serious leak inside the generator. A leak that results in a lot of liquid usually requires shutting down the generator for repairs. From time to time, the hydrogen inside a generator has to be replenished or replaced. The source of hydrogen may be a bulk storage tank, as shown in this illustration, or it may come from large gas cylinders. For our discussion, we'll be using cylinders for the hydrogen supply. A series of valves controls the hydrogen's pressure and flow. Before maintenance can be performed on a hydrogen-cooled generator, the hydrogen must be safely removed from the cooling system. Since hydrogen can be explosive when it's mixed with air, a procedure called purging is used. In this process, a non-explosive gas, which is usually carbon dioxide, is used to force the hydrogen out through a vent pipe before air is allowed to enter the generator. It's important for plant personnel to be familiar with the location and use of material safety information for hydrogen and carbon dioxide because of the potential dangers associated with these gases. Carbon dioxide, which is also called CO2, is supplied to the generator through piping similar to the system used for the hydrogen supply. One way of connecting these gas supplies is shown in this illustration. Carbon dioxide may be supplied from cylinders or from a bulk storage tank. With a bulk tank, a vaporizer is required to convert the CO2 from a liquid to a gas. A three-way valve is used to control the flow of all three gases, hydrogen, CO2, and air, that will be used in our purging example. Vent valves control flow through the vent pipe. A gas analyzer is connected to the vent pipe to provide a means of monitoring the purging procedure. The CO2 enters the generator through a manifold at the bottom of the casing. The heavier CO2 forces the hydrogen back through the upper manifold. From there, the hydrogen passes through the vent pipe to atmosphere. Outside, large quantities of air dilute the hydrogen safely. When the gas analyzer shows that there is less than 5% hydrogen in the vent stream, the CO2 is turned off and the air supply valve is opened so that air enters through the top manifold. The air then displaces the CO2, which is vented to atmosphere. Now the atmosphere inside the generator is breathable, and necessary service can be performed safely. When maintenance is complete, the purging process is reversed. First, the generator is sealed and pressurized with air for a leak test. Then CO2 is used to force the air out of the generator. Finally, the CO2 is replaced with hydrogen. The stator in a generator is made up of bars that carry current to the generator's output connections. This current flow produces a significant amount of heat, so larger hydrogen-cooled generators often have a separate cooling system to cool the stator. The stator is cooled by pure water that flows through hollow conductors inside the stator bars. Even though electricity is present, water can be used because pure water is actually a very poor conductor. It's the dissolved solids and impurities in water that cause it to conduct current. Stator cooling water is demineralized and filtered to keep it very pure and non-conductive. We can identify the major components of a typical stator cooling system using an illustration. This system is a closed-loop system. The water is recirculated after it passes through the stator bars. The first component is the water supply tank for the system. Next, there are two pumps. One pump is used for normal operation, and the other serves as a backup. A sensor at the generator outlet detects the temperature of the cooling water. If additional cooling is required, the sensor adjusts a temperature control valve that redirects the water flow through heat exchangers. A pressure control valve maintains the proper pressure in the system as the water is recirculated to the stator. This system also includes filters to remove magnetic particles and other contaminants. Another component in the cooling water supply system is a demineralizer. The water in a stator cooling system is tested for electrical conductivity, which is measured in terms of mhos. A mho is the opposite of an ohm, which is a measure of resistance to current flow. If the conductivity of the water is higher than 0.5 micromhos, or 0.5 millionths of a mho, it means that enough minerals have accumulated to allow current to flow through the water. If the water is becoming conductive, more of the flow is directed through the demineralizer piping, where minerals are removed and other impurities are filtered out. The supply of water is usually replenished when necessary through a connection to the plant's demineralized water system. If the stator cooling system is not removing enough heat, the load on the generator may have to be reduced. This is referred to as a stator cooling runback. Some systems are equipped with automatic controls to reduce steam flow to the turbine until the temperature within the generator returns to normal limits.